So the structure is such that I'm gonna take up drill problems first, and then I'm gonna go into just looping in Julia. So I'll talk about for loops and if statements in specific, and then I'll go into solving LU, factorization, decomposition in Julia, as well as in drill problems, and hopefully we can make the connection between the two. But before we go into it, I want to go over matrix multiplication, because that's in your drill problems, and I want us to be able to see how we're looking at rows and columns and how we're able to represent this n cross m matrix into this column vector that is 1 cross n, because it has a bunch of rows of m cross n dimension. So A1 row can be written as 5, 3, 8, and A2 column can be written as 3, 2. I'm going to go over these faster. If at any point there's a doubt, you're the only person here, so we can pace it to however you like. So then C is A times B. If we're going to do the standard matrix multiplication, we know that the formula is Cij is Ai row and Bj column. So I want to write down all of the elements of C and try to compute it using that formula. So I get A1 row times B1 column. This one is A1 row, B2 column, A2 row, B2 column, A2 row, B1 column. So A1 row can be written as 2 minus 4, 2 times 2, 6, 3. This is, I don't want to do the math. That's minus 14. A2 row is 3, 4, 8 times minus 5, minus 3, and 2. And then this becomes 3 minus 15. I'm just going to look it up. It's, if you check the math, it's 54. No, I'm sorry. Yeah, it's 54. Then C12 is A1 row is 2 minus 4, 2 times 5 minus 3 and 2 minus 5, sorry. And then this computes to 6. And then finally A2 row is 3, 4, 8. This is minus 5, minus 3, 2. And when you compute this, you get minus 11. So then our C matrix is minus 14, 6, 54, minus 11. Now I want to do the same, but I want to do it the second way of matrix multiplication that we learned. So we'll be summing over columns and rows. So C is AB times sigma I1 to K. Here it's worth mentioning that A is M cross K and B is K cross N, and that's what the K is. So by this algorithm, we get that the dimension of C should be 2 cross 2 and K should be 3. This means that I can reuse that formula and I can open this summation term and I can write it to be A1 column, B1 row, plus A2 column, B2 row, plus A3 column, B3 row. And then I fill it out from our solution and it comes out to be A1 column is 2, 3, B1 row is 2 minus 5, A2 column is minus 4, 4, B2 row is 6 minus 3, A3 column is 2, 8, and B3 row is 3, 2. And when I multiply these, I get 4 minus 10, 6 minus 15. Here I get minus 24, 12, 24 minus 12. Yeah. And then here I get 6, 4, 24, 16. And then I add it up and I get C is 4 and 6, 10 minus 24 minus 14. 16 minus 10 is 6. This is 24 and 24, 48, and 6, 54 minus 15. That is 1 minus 12 is minus 11, which is the same that we got from our standard matrix multiplication, just to prove that they're actually equivalent. Hopefully this was clear, because I am going to move on to LU, because this is going to take the most of our time here. So LU decomposition, we want to convert a system of equations into the standard formulation, which we have AX equals B. Now instead of doing the whole finding the determinant of A, then getting an inverse of A, the way that we're going to solve it is using LU decomposition that simplifies the structure of A and lets us solve for X a lot faster when you'll see in computation. So I think it's clear how to convert the system of equations into AX equals B. So I've just done that for us, and if there's any questions about it, you can take it up in office hours, and then you can go over it. But from this, we know that the dimension of A is 3 cross 3. It's 3 equations, 3 unknowns. And then in the beginning of the algorithm, you initialize K equals 0 and the temp variable that saves the value of A, so it should be a copy when you do it in Julia. Now, what I want to do is I want to go over different iterations of this algorithm till we get it. So at K equals, 1, because it starts in Julia with 1. So K equals 1, and temp equals A, and there's nothing in L and U. So let's get started. First iteration, I want to find or I want to update temp equals temp minus CR such that the structure is such that the rows, the first row and the first column is 0, and there's some random entries in here. So the way that we know how to do that is, first thing I'm going to define for the first iteration K equals 1, I get C, which is the first column of the A matrix, or the temp matrix actually. So the kth column of the temp matrix divided by the pivot. Pivot is again 1 upon, oh, not 1 upon. The pivot is the first element of this matrix. So it is, for our problem, 1, the first element of the first column of the temp variable. Let me write that down. It is temp k column of k. So that translates into the way that we've done it in class. We write as c, but we don't know what c is yet, so we write as c of k, but it's equivalent. And then you get c of k is 1, so that is the first element of 1, 1, 3. So this element is the pivot. Replace all of that in our solution, and we get c is 1, 1, 3, the first column of the temp matrix for k equals 1, into the pivot that is 1. So your c is actually 1, 1, 3. Now we update r. I'm not rushing along, am I?
No, you're good.
Okay. So let's get r in here, and then you want the temp matrix, the kth row. So for k equals 1, that means the first row of the temp matrix, which for now is A, which is 1, I want the orange, 1, 2, 1. So now that we have the C and the R, we're going to update our temp variable using that equation. So we get update temp equals temp minus C times R. Our temp is at this iteration it's 1, 2, 1. So it's probably 1, 1, 3, and that is minus 3, 4, 1, minus 2. This is our current variable temp, and then we get C was 1, 1, 3, and R is 1, 2, 1. So we get 1, 2, 1, 1 minus 3, 4, 3, 1 minus 2 minus. It'll be dimensionally the same, which is what we need it to be, because otherwise you can't really subtract stuff. So it becomes 1, 2, 1, 1, 2, 1, 3, 6, 3. And when you subtract it out, you get temp at k equals 1 is 0, 0, 0, 0, 0, which is what we wanted. And then the rest of the terms are minus 5, 3, this is minus 5, and then minus 5 again. So at the end of this step, we have updated our temp. We also want to update our L and U matrices. So L in its update rule becomes L, and then row-wise concatenate the C, and then U becomes the U, and then column-wise concatenate your next row, which is the R vector. So from here, I get my L, actually let's write it here. I get L is There's nothing in L for now, so it's basically just C. And then U is also empty, so now it has the value 1, 2, 1. Great. So that would be the first iteration of our LU decomposition. Then what you want to do is you want to go and update your K, and then we are into the second iteration. I want to redefine, just want to write down my temp here again. Temp is 0, 0, 0, 0, minus 5, 3, 0, minus 5, minus 5. From here, I read the pivot, which is temp, the kth column, the kth element of the kth column of the temp variable. So the second element of the second column which is 0, minus 5, minus 5, and the second element is minus 5. Note that this is not 0, so we're good. And then I write my C. C is the kth column of my temp variable, which is now this, divided by the pivot. And again, we know that the pivot isn't 0, so this is okay to do. This becomes 0, minus 5, minus 5, 1 upon minus 5, and you get 0, 1, 1. Similarly, we're going to update our R, which we noted was temp, the kth row of our temp variable at this iteration, which we see is for k is equal to 2, it's 0, it is 0, minus 5, 3. Now we're going to update our temp again. And this time the structure should be that there should only be one element in the last at temp of 3 cross 3. So let's see if that happened for us, unless we made a mistake. So temp right now is, I'm gonna get the orange. 0, 0, 0, 0, minus 5, 3, 0, minus 5, minus 5, minus C we found was 0, 1, 1, and R we found was 0, minus 5, 3. So then this becomes 0, 0, 0, 0, 0. First row will be all zeros, the second row will just be multiplied by 1, and so will the third row. Once we do it, we get all zeros here like before. These elements become 0, and also this column becomes 0, and then we're only left with a minus 8 in here. So we're good for now. Next thing in the same iteration we want to do is that we want to update L and U. Our L was this 1, 1, 3, and U was 1, 2, 1. So now my L is 1, 1, 3 with what my new C is, which is 0, 0, 0, 1, 1. 0, 1, 1, and then u is just what my u was before, and that was 1, 2, 1. And then what my new r is, which is 0, minus 5, 3. Great. Now that we have this, we're gonna go to our last step, and we keep going until the temp is all zeros, which is what we should hope to achieve in this iteration. So for k equals 3, when you update your k, I'm gonna write down our temp, which was just all zeros except the last entry, right? And now we want to find a C and a R. So my C is, for the last time, the kth column of the temp variable. Plus, oh wait, we forgot the pivot. So my pivot is kth row from the kth column, of temp. I'm going to pick out the kth element, and that will be my pivot. So in this case, kth row means the third, kth column means the third column, this 0, 0, minus 8. And the third element in there is minus 8. Again, it is not equal to 0, so we're good. So C is the kth column of temp divided by the pivot, and that becomes 0, 0, 8, minus 8, 1 by minus 8, which will be 0, 0, 1. Now I want to get my R. My R is the kth row of temp. K is 3, so it is the third row of temp, which is 0, 0, minus 8. Oh, let me move these out of the way for now. Right. So from here, I'm gonna update temp, and hopefully it is all zeros. So our temp is again is all repetitive, but that's why we can put it in a loop. Okay. So C is this, and your R is this. I make it so that this becomes all zeros again, and then 0, 0, minus 8. And from there, you know that this is indeed all zeros, which is what we wanted. So everything's good. The last thing left to do is we want to update our L and U. So I'm going to write down L, the current value with the row. We last left our L at 113,011. So 113,011 times, and then concatenate what C is, which is 0, 0, 1. Similarly, U is whatever u was, and then add the new row. U in our previous iteration was 1, 2, 1. Zero minus 5, 3, and then this time we add 0, 0 minus 8, which is our r. So that is how we are able to decompose our A into L and U. And I want us to also be able to check that, not take our word for it, and there'll be, like, you'll see a pattern in there. So let's confirm that A is indeed L times U. So what was my A? Let me look it up. Do I have it here? Let's just scroll all the way back and find what A was. Okay, so it is 1, 2, 1. Wow, we wrote a lot. Okay, so my A is 1, 2, 1. 1 minus 3, 4, and 3, 1 minus 2. Okay, and my L is 1, 0, 0, 1, 1, 0, 3, 1, 1 times 1, 2, 1, 0 minus 5, 3, 0, 0, 8. And then we see this row. If you do the normal row-wise multiplication, you get 1 times 1. Here you get 2 times 1. Then this one is 1. Again, because these two are zeros. Oh, this was 2. 1, 2, 1. Then for this row, with this column, you get 1. For the second row, second column, you get 2 minus 5, which is minus 3. Then for the second row, third column, you get 1 plus 3, which is 4. For the third row, first column, you get 3. For third row, second column, you get 6 minus 5 is 1. In third row, third column, you get 3, and 3 is 6. 6 and 8 is 6, and this one should be minus. Yeah, 6 and minus 8 is minus 2. Yeah, I copied it wrong. It was minus 8. So then we've confirmed that LU indeed works for our problem. And we found a way to convert a matrix that had no structure to it into a product of a lower triangular and an upper triangular matrix. And now, from our past lectures, we know that we're able to solve triangular matrices a lot more easily than we're able to solve like the general structure. So if we're clear on that, I'm going to go ahead and finally solve for x.
Yeah.
Yeah? Okay, good. Are you
I get
waiting
it.
for me? Okay, you're good. Okay. So if you see in the appendix, and this is from our class notes, we're going to use the general structure of forward and backward substitution. So the first part is the forward substitution. And I'm going to replace n equals 3 in here. And I already have these formulas up. So let me just move those into context. And these are easy to get from our general solution if you just put n equals 3, which is your dimension. And then from these formulas, I want to be able to solve. First, I'm going to solve ax equals b that we've written down as L times u equals b. And then we called this y. And we said L times y equals b. And then this I'm going to solve using forward substitution. Why? Because it is a lower triangular matrix. So now that we have our L and U, just gonna put those in there. You get my L. Let's actually before define our variable y. So let y equals, x was EFG, y can be CD, EFG, H, IJK. So from that general solution, I get I is equal to B1 by A11, which in our case, oh, I actually need the B down here too. Let's get the B down here. I don't want to scroll all the way back. Yeah. So the B from our system of equations was 13 minus 9, 9. So let's write that down. I know B is 13 minus 9, 9. I'm going to put these out there. And Y is some HIJ is what I've used. And then we know L, because we just searched for it, we just found that out. And I'm just going to use the formulas that we derived for forward substitution. And then you get H is B1, which is 13 by A11. A in this case will be from our L matrix. Let's just also write L here. So L is 1, 0, 0, 1, 1, 0, 3, 1, 1. So A11 is the first element of L, and that is 1. Then I is B2, which is minus 9, minus A21. So A, the second row, first column is 1 times x1 is H by A22. I don't know how the 22 got here. So A, the second row and the second column, the element of the second row, second column of the L matrix, which is 1. Then you replace your value of H in there, and you get minus 9, minus 13, which is minus 22. Then you get J equals B3. B3 is 9 minus A31 is in the third column, third row, first column, which is 3 times x1 which is h minus element from third row, second column, which is 1 times x2 is I by A33 is the last element of L, which is 1. So this becomes 9 minus 3 times 13 minus of minus 22. So then 9 minus 39 is minus 30. Minus 30 plus 22 is minus 8. So then from here, you get y equals hij, which is 13 minus 22 minus 8. Now from this example, this equation, we know that ux is equals y, because that's what we substituted in there. So your next set of equations is ux equals y. You already have the y up there. I'm going to write down the u. U, from what we found in our example, is 1, 2, 1, 0, minus 5, 3, 0, 0, minus 8. We know our y and our x is our vector of unknowns, which in this case I'm calling EFG. Now we note that U is an upper triangular matrix, so for upper triangular matrices, we do back substitution.
Could I solve this a different way? Like I actually write out the write out the matrices back into a system of equations
Yep.
and then solve that.
Yep, that's even a better way to do it,
Okay.
because that's more intuitive. The only reason we're doing it this way is because we want to see the structure of how to use our B1 and how to actually write it in a program. But when you're doing it by hand, yes, that's how I would do it.
Okay.
Yeah?
Yeah.
Okay, we have Sejal here as well. I think she's here for the Julia stuff, which we're gonna get to in 5 minutes. So once we do this back substitution, I'm gonna find x1, x2, x3 using those equations. I'm gonna get x1 is b1, x1 is actually e. E is b1, which in this case is y. So the first element of y is 13 minus, actually let's do it your way, just so I'm not confusing you. So ux equals y. Let me multiply this, and I get the set of equations that are e plus 2f plus g equals 13. And then I get minus 5f plus 3g minus 5f plus 3g equals minus 22, and then I get minus 8g is equals minus 8. Then, because I'm doing backward substitution, I'm going to use from 3. I get g equals minus 8 by minus 8 equals 1. I use that and I put it in the second equation. I get minus 5, or let's just put it that way. I know that f is minus 22 minus 3g by minus 5, which is minus 22 minus 3 by 5. And this is 5. And then from my first equation, I'm trying to find the e. I take all the terms to the right-hand side. Minus g, which is 13 minus 2 times f is 5. And g is 1. So 13 minus 10 minus 1 is 2. So from here, I get the solution x equals 2, stack them in the opposite order, 2, 5, 1. And that is our solution. If we were to go back and check if ax is indeed b, you will get the right answer, but I don't want to go into it. You should try it, that we actually did solve it. So that covers what I wanted to go over in drill problems. And hopefully that helps you with homework 3. Do you have questions before I move on to the Julia part?
No, I'm good. Thank you.
You good? Sejal, you're good?
Yeah, I'm good.
Okay. So I'm going to move on to Julia then. I'm going to need my keyboard. Okay. Right on time. Let me open it locally. Didn't download it. Give me a second. It was on the other computer, so I'll have to find it on Canvas. And hopefully you guys have that notebook as well. So get to my files, Recitation, today. And yep, I download this. Amazing. Then I go in my downloads, and there you go. All right. So today I want to take up control flow in Julia. So we're going to talk about what we've done as of now is we've been able to describe vectors and matrices, and we've been able to do computations, but you've noted that you don't jump around or you don't repeat a part of your code ever. It's just line after line after line that is being executed. But a lot of the times we're going to be either wanting to jump to different parts of our code, or we're going to want to execute different parts of it based on if they pass certain conditions. And the way to do that in Julia or any programming language actually is using control statements. And the most common ones are for loops, while loops, if-else loops, and a lot of them also have do-while loops. For the purpose of this lecture, though, we're going to stick with for and if-else. So for loop, you want to use for loops for situations where you want to repeat a process or a part of your code multiple number of times. And you should also know the number of times that you want to repeat that code, or you should at least know a stopping condition. The basic syntax for this is you want to define what's called an iterator. So in this case, our iterator is I. Then you want to use the keywords for and you want to use the keyword end so that you know what is the block of code that you want to repeat in that loop. So everything between the for and the end is going to be repeated 10 times because I goes from 1 to 10. So this 1 to 10 is your condition or your range for the iterator in the for loop. So as you would expect, if I run this block of cell, I should get different values of I at, amazing. Wait, let me get the kernel. It gave me an option. I didn't like it. This is, yes, I need the kernel. Yes, sorry. So now that I will finally, eventually execute this, I should essentially see the different values of I at each iteration. It will go from I is equal to 1, print I, update I, print I, update I. And the kernel is still starting. Wonder if it's easier to do on the Lumi. Is it my internet or? Okay, yeah, okay, we're good. So at each iteration, all it did was it executed this show statement, which literally just prints I equals to whatever the value is. Then you can also have what we call nested loops, in which case you will have something like this. You'll have this block of code being run 4 times for each value of I. So for I equals 1, you run the whole block. For I equals 2, you run the whole block. Then there's another for loop inside, which makes this part of it run 2 times for j equals 2 and j equals 4. So what you should essentially see, say in the first iteration, is I equals 1 times. So when you start, you're going to see, and writing this down usually helps. It's called doing a dry run for CS people. So for I equals 1 and j equals 2, you'll get I times j equals 2. So the first input should be the 2. Is this doing this to me? Amazing. Okay. Yeah, I don't know why this isn't working today. Okay. I times j equals 2. And then the next iteration, you'll always have the inner block do its iterations first. So you'll have I equals 2, I equals 1. I think it's about like, yeah. And j equals 3. Then you get I times j equals 3. And you keep going like that. And then finally, when you hit j equals 4, it goes back to updating I, which is I equals 2. And then you keep going till I hits 4 and j hits 4. So your output is going to be, I hate this app. Yeah, your output is going to be for I equals 1, j equals 2, 2, then I is 1, j is 3, then you get 3, then 1 and 4, 4, and then 2 and 2, 4, 2 and 3, 6, 2 and 4, 8, and then so on. We're good? That's like the basic function of how you do like nested for loops, yeah?
Yeah.
And then for Julia specifically, you don't have to write like 2 for loops, and this way is a little unclear, but it'll do the same thing. It's the exact same output, it's just a different way of writing it down. You can just put like a comma instead of saying that I want to iterate in a nested fashion. So that's like the basic for loop. What you're doing in there though is you're specifying something to run, like you're specifying ranges. So there's like different ways of building ranges which are specific to Julia that we can go into. One is the standard I step 3 and 10. So the first element will be 1, then it will step 3 and you'll get a 4, and it'll do it until 10. So the first is 1, add 3 because that is your step, instead of just 1 is to 10, which is 1, 2, 3, 4, and so on. The step is 1 implicitly. So you get this output. There are other ways of specifying ranges. In fact, it may be helpful if we do question mark and just range. So there's different options. There's the simple range, there's the simple linear range, unit range, step ranges, and all of them will essentially do the same thing. You can also specify a range like range 1 comma step is this and your length is this, and it'll give you this range, like 1 is to 5 is to 496. And it's pretty self-explanatory if you want to look into it. I'm going to take an example of what a unit range is. And it's essentially just 1 is to 10. So the step for a unit range is specified to be 1. There's no actual significance to it, but it's just like a second way of writing stuff. And you can specify stuff like data type and just be better about it. You should also know that the way that Julia does it is that you can access properties of these elements. So you can say, I want to see what the start of this range is, and I want to see what the stop of this range is. Sometimes it's useful when you're running through your loop just to see, what the starting iterator was and like specify conditions to it. So I think that comes in handy where you don't have to keep track of things in your ranges. Another comparable way is just simply specifying the range like we did in our for loop, just 1 semicolon 10. And you will see that the two types are completely the same. So when you say unit range this and saying this, it essentially means the same thing. So A is equal to A1 is true. You can also see that the type is essentially same. So when you're telling Julia this semicolon operator and you don't specify a range, it is going to read it as an element of this unit range structure. There's another way of doing it. Let me actually look it up for you guys. Linear ranges, which comes in handy in programming sometimes. So let's say you want a range of variables between minus 0.1 and 0.3, and I want 5 variables in there. So I'm going to use a linear range function. So In this example, I'm saying I want 6 numbers between 1 and 10 that are exactly equally spaced. So I get 1, 2.8, 4.6. So I get exactly 6 numbers that are equally spaced between 1 and 10. And it also comes in handy, and it's just a good thing to know. Then you can access like the different, so the 1 is the start, the B is the B dot stop is 10 for our problem, and then the length, the B dot length that we specified is 6. So when I run this, I should get 1, 10, 6. So there's like different ranges, and depending on what you need for your problem, you can specify them any way that you like. Now, one thing to note here is that this definition is a lot similar to how we used to access our arrays, right? We just say A of 1 to 10, and that'll give us like the first 10 rows or like the first 10 columns of A. So we want to see if arrays are really any different. So I specify an array, I call it my array. And then we do the normal way of specifying a range, and I am able to extract the first 10 rows, which was expected. But then, do you remember we specified A is unit range, this thing? You can also use A to access the same thing. Now you will also note that when I display A, it looks something like 1:10. And then I'd ask you, and you'd say, maybe it's not an array, but Julia can interpret between these things. And I can actually access the 4th element of a range like it was an array. So I can just say A of 4. And A, even if it's a range, I can access like the 4th element of it. Another function for building arrays from ranges that you've probably seen in your homework is using the collect function. So I use the collect, and I give it a range, and it doesn't, like, do you remember when we did A equals 1 to 10? This is what it returned. It was still a range. It wasn't an array. If you want to convert it into an array in one step, you want to use the collect function. Are we clear? Yeah, perfect. Now, another way to build arrays from your for loops or from your ranges is using this one-line version of a for loop. You will also notice that it doesn't have the end keyword, and it has this in keyword. So what this will essentially do is it will look at this part and it'll say, okay, this term, and it looks at, okay, what is I? And then it gets the I from the second part of it, as for I is in the range 1 to 5. So this is equivalent in math to saying that I belongs to the interval 1 to 5. And it will compute this expression that is add 0.1 to all the elements and return that to us in an array. So your comp vector will be for I equals 1, 1.1, for I equals 2, 2.1, and then so on till I equals 5. And this is sometimes helpful when you want to construct, like, let's say you don't want to use a function and you want to get the first 10 elements of a sine wave in a particular range. So you just go, instead of I plus 1, I just say sine of I, right? Don't know if it'll run, but let's see. Yeah, so I get sine of I from 1 to 5, and that gives me an array of it. So I think it's pretty handy, the structure. And it's a good thing to know. Now, we know from the for loops how to run a segment of code a given number of times and get the input and then manipulate it. What if we wanted to run a segment of code only if it passed a condition, and that condition is not a range. Your condition isn't like I is greater than 1 and I is less than 10. Your condition is something more complex. There I can say, let's say, if followed by, you don't have to use the brackets here, I just happen to use them. If A, the fourth element of A, if it's equal to 4, then show what A was. And then it's like the simplest way, the simplest if condition that you could have written. Something a little more interesting is, I define my x and my y, and I want this block of code to tell me in words if x is greater than y or if x is less than y. So I simply get if x is less than y, so if 10 is less than 4, execute this statement, and if this condition is not true, which essentially means if x is greater than equal to y, the complete opposite of x is less than y, then you want to execute this statement. Just basically tell me that. So when I run it, I know that 10 is not greater than 10 is not less than 4. So it tells me that x is greater than or equal to y. So that finishes if and for, but before we finish if, we want to understand, like this was a simple condition, and if you run this, it gives you something like, if I say x less than y, it'll be a Boolean, so like a logical expression. The way that you want to be able to work with your logical expressions is there's operators to work on it, to modify them, and these operators are called logical operators, and there's 3 of them. There's not, and or. The not operator is a unary operator. So let's say I wanted to change the logic of this code to the wrong logic. So now this will give me the wrong solution. It will say, if x is not less than y, then do this, which shouldn't be the case. Like x is not less than y. So that was the bad code. So, logical operators. Not operators simply negates what you have. So something like this, so true is false and false is true. A condition that evaluates to true can then become false. Next thing is the AND operator. So you want to use the AND operator when there's 2 conditions that should simultaneously hold true for a part of your code to be run. So I say true and false. One part of, it'll only be true for true and true. So let's try and see that. Everywhere else, it'll be false. You can't have any of the conditions be false. Both of them have to be true. So in something like this, you see if is 2 equal to 2? Yes. If is 1 less than equal to 1? Yes. So this expression should be true. And similarly, let's say this one. Is 2 greater than equal 0? Yes. And true. And this will evaluate to true again because both of them are true. But if this was, say, is 2 less than equal to true, if this was false, this will be false. Similarly, if there's a condition where you want to execute a block of your code, depending on either one of the conditions holds true and you don't care about the other one, like let's say you were to say that I'm going to do this thing if I'm going to do my homework, if I go to the recitation, or if I go to the lectures. Otherwise, I'm just not going to do it. So you want to use the or construct. So you do either of those conditions if they're true. You want to run that segment of code or do the homework. So true or anything really will always be true, and a false is the only thing that will give you a false. We could also chain multiple expressions. So for this one, if any of these conditions evaluates to true, it's going to give us a true. So is 2 equal true? 2 equals to 2, you get a true. Then it's pointless to look at any of these and you get a true. If 2 is less than 3, 2 is indeed less than 3, so both of these should be true no matter what's coming after the true condition. So they're both true, which makes sense. So we've learned how to specify conditions. We've learned how to specify multiple conditions, different arrangements of it, different ways to operate in it. We've also learned how to repeat a segment of our loop, write for loops. Last thing we want to do is we want to be able to run a combination of these structures. And a very common way of doing that is you want to write, you want to run through a for loop. What we're going to do right now is we're going to run through a for loop, and it's going to have an if in it. So we're going to do something special for a special iteration of your for loop. And I'm also going to introduce the break keyword. The break keyword does what you would expect. It will stop the loop whenever it sees the break word. So let's say you're inside a loop, you're running a couple statements, it sees the word break, and it will go to the statement after your end of your for loop, the end statement. So we're going to use the structure to write down a program that should return if a number is prime or not. So prime numbers are just numbers that don't have a divisor other than the number itself and 1. So I'm going to give the number input right here. Let's say I want to check if the number 19 is a prime. So what I want to do is I want to check if all the numbers leading up to 19 divide the number 19, and if any of them does actually divide the number 19, I'm going to say, okay, this number is not a prime, and I will exit out of my loop. So the way to do that is, first of all, I'm going to iterate over all of my numbers, starting from 2, leading up to the number 19, because 1 divides everyone, right? So I go from 2 to whatever my input number is. Then I say, if my number, when I divide it by all of these numbers, if at any point my number is divisible by any of these numbers, that is, the modulus of that equals 0, I know that it's not a prime number. So I will display that it is not a prime number. And at this point, I don't want to keep going through the loop, looking through the rest of the number. If I have reached a point, let's say this number was 25. At I equals 2, this will not be true, but at I equals 5, I will find that this is indeed true. It will say that the number is not prime, but once it's set that, it's pointless to go through the rest of the loop. So I will say break. What this break will do is it will take us out of this loop, and you will reach this line number 14, line number 13, 14, essentially. But another thing to note is that if this block of code never executed through all of this range, we know that your number is indeed a prime. And this should be number minus 1, because 19 divides 19, right? Let's try with 19. So we know that 19 is a prime number. Let's try and see if our code is correct. So one thing to note here, though, it should have been like outside. We need another if statement. Otherwise, it'll always keep telling you prime number, prime number, prime number. We can try, let's see 25 with this bad version of the code. 25, it ran through it for 2, for I equals 2, it said, looks like it's a prime number. Then it went to I equals 3, it said, okay, it looks like it's a prime number. But then finally when it got to I equals 5 and it divided it with the 5, it got, oh wait, 5 can divide it. That means it is actually not a prime number. I'm going to leave the bad version of the code. It's fine. So that is one way where you can control the flow of your code, and you can, in a way that it makes sense. Now we want to go through matrix multiplication using loops. I'm going to do it quickly because we're running out of time. I define my A, and I want to define A times B. The code for this, you should try and write this with me, but what you want to do is, for each of the elements, so for each Cij, I'm going to need to iterate over the rows multiplied by the columns, right? So I get for I equals 1 to 2, and j equals 1 to 2, I get C of ij equals A, the first row of A, which is, and then transpose it because Julia returns column vectors, and then B times the jth column of B. And that should be my I equals j, my A times B. And then I want to see what my C actually turned out to be, which is what we did in the drill problems, and we can confirm that that is indeed true. Let's try and write the code for our column-wise multiplication. We know that the structure is, from our drill problems, it's sigma k times, if I remember it. Yeah, so your structure is, if it's m cross k cross n, then your loop should run k times. I'm going to initialize my C to be a vector, to be a matrices of 0. And I'm going to go from I equals 1 to 3, which is our k for this case, m cross k for the A matrix. So you get k is equal to 3. Then you get C is equal to C plus AI column and AI row. So I get ith column of A, which is A, ith column of A times ith row of B, and then transpose it because I need a row. And that should be it. I should be collecting C at every instant. I started with a 0, and it should keep summing them up. And I want to see what my C was, so let's put that there. And it is the same. So your row-wise and your column-wise multiplication gives you the same result, which is what it should be, right? We're following?
Why do you have to transpose the matrices?
So if I don't, you have to remember B of, say, 1 comma this thing. So you think that it'll give you like a row, right? But when you run this, it gives you a column vector. But what I needed was a row, but it's just that whenever you index your variables and it sees, okay, this is a vector, and then all vectors are columns.
Okay.
But I really wanted like a row, so I need a transpose, and then if this runs, I have a row.
And also, why do you have to hard code the numbers like for I equals 1, 2, 3? Is there a way to like get the length automatically?
What? Can you be louder?
Yeah, for like in the for loop you have for I equals 1 colon 3. So is there a way to, I don't know, directly get the length of the matrix from somewhere instead of actually writing 3?
Oh yeah, there is. I just didn't want to confuse you. So you get size of A, comma 2, and let's check if that is the case. You want to see the C? It's the same thing. So you extract the second dimension of A or the first dimension of B, and that is your kth element. That is your K.
What is the dimension again? Why do you have to put a comma 2?
So yeah, let's see. So this is M. This is not going to let me write. Okay, let's go here. So in here, your A is M cross K and K cross N.
Yeah.
So if you look at this one, your A is 2 cross 3, and your B is 3 cross 2. So your M is 2, your K is 3. K should be the same, right? For you to be able to do the multiplication. And then your N is 2. And then your C should be M cross N. But you go from 1 to K when you're going column-wise. When you're going row-wise, it doesn't say, but you're going to need to go like every element. Is that clearer?
So, I mean, you still kind of have to hard code at least one number into the code.
So if you look at this one, it's easy to see that your K is 3, right?
Yeah.
So then when you open this expression, for K, keeping in mind K equals 3, you get A1 row, B1 column, A2 row, oh, the thing that you have written down here actually. And we end at 3 because we only have to go to K equals 3.
Okay. Yeah.
If you're confused how to like intuitively see that, it is because you want to get this multiplied with this thing. Where is it? Yeah, this column with this row, and then this one with this. So 1, 2, and then this one with this one. So that's 3, right?
Mm-hmm.
Okay. If it's still not clear, hit me up. Yeah? Amy, is it clear for you?
Yeah.
Okay, good. So now we know how to do matrix multiplication in an impromptu manner. This, I'm going to get into LU for the same system of equations that we had. I don't know where this went, but it is for the same system of equations. If you compare the A with the A that we got here, it's 1, 2, 1, 1 minus 3, 4, 3, 1, 2, 3, 1 minus 2, which is what I put in the M. Then we went through our algorithm and we found the steps. The first step is initialize K equals 1. So we get K equals 1. Then we said your C is the kth column of temp, and your temp we defined as a copy of A or M. Then you get C. Oh, the way that we're going to do it here is they get C is the kth column of temp. Then the pivot is the kth element of C, which is what we saw here. It's the kth element of their temporary C, which is essentially temp, the kth temp of the column. The full thing. And then C is C by pivot, and that's their final C, and we did that in one step. It's either way is fine. Did I confuse people, or is this okay? I'm going to assume it's okay. So you get the C, and then we know K is the rth row of the temp vector, of the temp matrix, right? That's how we did our drill problem. And then finally, we want to update our L as a row concatenation with whatever column you get next, and then U as updating the next row of U. So this will be this updation that we're talking about. Now that we have that, we want to update our temp the same way we did in here. Temp is temp minus C times R. And we should look back at what we got. We got temp is this thing, and L and U are 113 and 121. And this is what our block should give us.